Okay, this is the second video for section 7.9, the building up principle, also known as the Aufbau. Basically, my friends, what we're going to do is we're going to use the information that we came up with or that you learned in the previous video to begin to write electron configurations using the periodic table. The method of electron configuration writing that we're going to be used is what I consider to be an abbreviated method, because we're going to represent the core electrons, the inner electrons, using a symbol to represent them. And we will only represent the configuration of the outer electrons, the ones in the outermost shell, or also known as the valence electrons. So let's say, for example, we want to write the electron configuration for the element nitrogen. Okay? Now, what we're going to do is we're going to work our way backwards from nitrogen to the noble gases that are here on this side of the periodic table, right? Here are the noble gases. So we're going to start at nitrogen. We're going to work our way backwards to the noble gas that comes before nitrogen, which is helium. So nitrogen now has the same core as the noble gas helium, which we're going to represent by putting helium in a set of brackets like this. So we're saying that nitrogen's electron configuration has the same core as the noble gas helium. So we start with helium. But of course helium is not nitrogen. We haven't reached nitrogen yet on the periodic table. And so what we have to do is we have to start here at lithium and work our way across from lithium over to nitrogen. So when we get to lithium, we know that lithium is part of the S block. And we know that these atoms are filling s orbitals, right? And they are s orbitals in the principal quantum number, which is equivalent to their period. So in other words, after helium, lithium fills the second energy level s orbital with one electron. So we go to lithium. Then we move on to beryllium. Well, it's also in the s block, so it's filling the second electron in the s orbital. So that represents 2s2. So nitrogen has a helium core plus 2s2. 1 as we go from helium to lithium, and then 2 as we go from lithium to beryllium. Now, we're not quite at nitrogen yet, so we have to continue on doing what we're doing and moving forward in the periodic table till we get to nitrogen. So, as you know, these guys are filling the P block, right? And they fill the P block of the principal quantum number, which is equal to their period number. So these guys are filling 2p. Beryllium represents 2p1. Carbon represents 2p2. And now nitrogen is the third electron, so it's 2p3. So nitrogen has a noble gas core of helium and 2s2, 2p3 as its electron configuration. Let's try another example, shall we? Let's go on to, let's say, we do sulfur here. Let's do sulfur. Whoops, sulfur's moving. So let's do sulfur. So sulfur is going to have a core equivalent to the noble gas that comes before it, which is neon. So we're going to write the noble gas core as neon in brackets, right? Now, remember, it's all the way over here in the P block, but to go from neon through all the way to sulfur, we have to go through the S block first. So it's going to be filling S of the principal quantum number that's equivalent to the period number. So that's 3s. So as we go across, 3s1, just like sodium, and then 3s2, just like magnesium. But we're not there yet. We're not at sulfur. So sulfur now is sitting in the P block, and remember the P block is going to be filling the same principal quantum number as the period number. So it's filling the 3p. So to get across to sulfur, aluminum fills 3p1, silicon fills 3p2, 3p3, and now at sulfur, 3p4. So sulfur has an electron configuration the same as neon, the core of neon, plus 3s2, 3p4. Let's do something in the transition metal area, shall we? So let's do something in the transition metals. Let's go with, let's say, iron. So let's do iron right here. Iron. Remember, following the Aufbau. So we go back from iron to its noble gas that comes before it. So that means iron has a noble gas configuration of argon, right, in its core, plus, remember this is the S block, and the S block we said is filling the principal quantum number that's equivalent to the period number. So the period number is 4. This is the S block.
Jimmy Athenius, please report to the main office.
I hope he makes it there. Anyway, as you can tell, I'm at school. So we're filling the 4s and 4s1, just like potassium, then 4s2, just like our good friend calcium. Now, remember we said that the transition metals fill the D block, and we said it was going to be the D block of the energy level before the period number. So it's not filling 4D, it's filling 3D. And we count over. 3D1, 3D2, 3D3, 3D4, 3D5, and now to iron, 3D6. You see, there's no coincidence that we have 2 columns here, because they're filling the S. We have 6 columns here, because they're filling the p orbitals. And there's 10 columns here. No coincidence that there's 10 columns, because they're filling the d orbitals. And that's basically how the periodic table is set up. Excuse me. It turns out that the periodic table ends up being set up based upon the Aufbau. Not a coincidence, but not planned that way either. So let's do another one. Let's say we're going to do arsenic here. As, arsenic. So we go backwards to argon. So arsenic has the same noble gas core as argon. So that's its noble gas core. And then it's going to start filling 4 because it's in the 4th period. And it's going to go through the S blocks, 4s1, 4s2. Then, of course, it's going to start filling the Ds, but it's of the energy level before. So it's D1, D2, D3, D4, D5, D6, D7, D8, D9, D10, right? 10 columns. And now it's filling the p orbitals because it's in the p block. And, of course, because it's in the 4th period, that means it's filling the 4th energy level, p block, 1, 2, 3. So arsenic should be argon 4s2, 3d10, 4p3. Okay, let's take this down a little bit further. Let's go right down to the 6th period and give you a little explanation about what's going on down there in the 6th period, because it's a little bit different. You see, when we get to the 6th period, we start off with cesium, which is filling 6s1, and barium, which is filling 6s2. But you'll notice these lines tell us to jump down here to the lanthanide series. Okay, as we were saying, we are here at cesium, and as we go across through the 6th period, we actually have to go down to the lanthanide series. So this is going to fill 6s. Now, as we said in the previous video, this is the F block. So as we go across, we're actually filling the F. But something about lanthanum is significant. Lanthanum actually belongs here in the D block. So as we go across, we fill 6s, and then we go with the lanthanum, we actually fill 5d. So we put 1 electron in the 5d, and then we go from lanthanum to Ce. Now we're going to fill the 4f, and as we come back up, now we go back and start filling the 5d again, and then the 6p. So let's pick an element out here in, say, the 6p, and I'll show you exactly what I mean, okay? All right. So let's get rid of this. Boom. Let's get rid of this. Boom. All right. So let's say we pick bismuth right here. Bismuth. Bismuth electron configuration. So we're going to run backward from bismuth to xenon. Xenon is the noble gas that comes before bismuth. So bismuth has a xenon core. So as we run from bismuth across over, as we run from xenon across over to bismuth, we're going to start with cesium, right? So cesium is in the 6th period. Need to move that over. There it is. There's the 6th period, right? Whoops. 6th period. Try it one more time. 6th period. There's the 6th period. So it's going to fill 6. And this is the S block, so it's going to fill 6s1, 6s2. Now, from there, we said we don't go straight across, because if you look at the atomic number for barium, it's 56, and lanthanum is 57. So we've got to go from 56 down to 57, 58, 59, 60, because remember, it's filling the Aufbau. 55 electrons, 56 electrons, 57, 58, 59, 60, and so on. Back up to here, hafnium, where we get through 71 down here. Back up to hafnium, where we go 72, 73, 74, 75, 76, and so on. So we're filling up 6s2 with cesium and beryllium. I'm going to jump down to lanthanum. There's that bell, which is technically in 5D1. And to go from lanthanum to Ce, now we're starting to fill F. But remember, F is of 2 energy levels less than our good friend the period number. So we're going to fill up all the 4 F's all through loop LU here. That's going to get us to 14. Now we're going to go back to HF, and now we're going to start filling again the D's in the 5th energy level. Because remember, this is the D block, and it's filling up the D of the energy level before. So we've got to go through the 6S, then we've got to fill 1 in the 5D, and then skip over to the 4Fs, go fill up all the 4Fs all the way across. Now we're back up to the 5Ds again. So hafnium is 5D2, 5D3, 5D4, 5D5, 6, 7, 8, 9, 10. So now this becomes 5D10. All right, so we've got 6S2, 5D10, 4F14. Bismuth is filling 6P. So since I'm kind of running out of room over here, I'm going to write it over here. 6P over there, and we're going to go 1, 2, 3. 6P3. And that's how you go with doing the lanthanum series, or the lanthanide series. Okay, now this video is running a little bit long. I'm going to try to shorten this up. I'm going to do 2 abbreviated versions that are exceptions to the rule. Okay, boom. And one more time. Boom. All right, exceptions to the rule. The chromium family is one exception to the rule, and the copper family. There are lots of exceptions to the rules, as it turns out, my friends, but these are 2 families in which we're going to show you these particular exceptions to the rules, and those are the only exceptions that you really need to know. So if we're looking at chromium, chromium should have an electron configuration of argon as its noble gas core, and then 4s, 2, because chromium is in the 4th period, and then 3D, 1, 2, 3, 4. 3D4. And that should be chromium's configuration. It turns out, based upon evidence, it's not chromium's configuration. So what is chromium's configuration? Chromium's configuration is actually Cr with the argon noble gas core, argon, come on, 4s1, 3d5. We notice that the S, instead of having 2 electrons in it, only has 1. And the D, which formerly had 4, now has a total of 5, giving us half-filled s orbital and half-filled d orbitals. For some reason, this increases the stabilization, or lowers the energy state, technically, of this particular electron system. And as it lowers the energy state of this particular electron system, it's more favorable. And for some reason, it does that for chromium, and chromium is an exception to the rule. So we've got one more exception. I'm going to try to do this quick before we run out of time, and that would be the exception for copper, the copper family. So as we go backwards, copper has a noble gas configuration of argon, right? And its electron configuration should be, as it's in the 4th period, so it's filling the 4s2 right? The S block, fourth period, and then 3D, because it's filling the D, it's in the D block, and it's the D of the energy level before. And we got 1, 2, 3, 4, 5, 6, 7, 8, 9. Should be 3D 9, but it turns out it's not. What is it? Well, I'll tell you. It's actually argon 4s1 3d10. So it's 4s1 3d10, and we see that S doesn't have 2 electrons anymore. It has 1, and the D, which formerly had 9 electrons, now has 10, because that 1 electron's been brought up to the 10. Now the S is half filled, and the D's are all filled, and that lowers the energy state of this electron system. Therefore, it's a more favorable electron configuration. Okay, well, I'm going to stop right here. Hopefully this will upload to YouTube no problem. And have any questions? See you in class. Bye.